Okay, earlier we have come across with a derivation which is correcting drift velocity, mobility of the electron, resistivity, relation between resistivity and uh, relaxation time, and resistivity, uh, and then it is conductivity. So there are resistance, connecting number of electrons, and relaxation time, resistivity, connecting number of electrons and relaxation time, and conductivity. So now, so here we are having the formulas and another form of the Ohm's law, that is J is equal to sigma E. Electric density is equal to uh, the conductance and electric field. So this is another form of Ohm's law. So from there we have extracted all these formulas here. So these are the formulas to be remembered from that derivation. So many formulas we got from the derivation. Very important formulas. Only if you don't remember the derivation, it is necessary for you to remember these formulas. How to remember these formulas means not by just what you call it as learning it as you learn the table, seventh table or eighth table, like that. So we have to do the numericals, the problems basing on this formula, so that you can understand what is n, what is E, what is capital E. This is what is this E? It is charge of the electron, electric field, relaxation time, mass of the electron. So like this, and here number of the electrons per unit volume, resistivity, and relaxation time, conductivity, relaxation time, resistivity, electric density, and conductivity, electric field. So whenever you go for a practice, then you can uh, remember these formulas well. So that is the way how to remember the formula. So now we will be having some numericals based on simple numericals based on these formulas. So here a problem is given. Find the mean time between collisions. What is the meaning of this mean time between collisions? So from this you can understand by definition, the mean time of the collision is relaxation time, tau, represented by tau. So this you have to find. Given the rho of the curve, that means here actually resistivity should be there. I can't write it as a word, so I just give it a symbol. So the resistivity is 1.7 into 10 to the power of minus 8 ohm meter, and number of free electrons per unit volume N is 8.48 10 power 28 per meter cube. Per meter cube it is as a unit, so no need to worry about that. So it is 8.48 into 10 power 28 per unit volume. So no need to mention the units also there. So these, and the mass of the electron is also given. It is 9.1 into 10 power minus 31 kg. Sometimes this will not be given and you have to remember it. Charge of the electron, mass of the electron, you have to remember it. Okay. So here these are these equations, and we know that E is 1.6 into 10 power minus 19 coulomb. So now, what is the expression connecting tau, rho, n, m, e? So what is the expression here? Just look here. So among this here, this is your resistivity is equal to m, n, e, tau. So just use that expression here. So rho is equal to m by n e square tau. So we want this. So tau is equal to m by n e square and rho. So what is m? It is 9.1 into 10 power minus 31. What is n here? It is 8.48 into 10 to the power of 28, and e square 1.6 into 10 to the power of minus 31 whole square, and rho is 1.7 into 10 power minus 8. So by just calculating this, we are going to get the answer as 2.46 into 10 to the power of minus 14 and you have calculated the tau. This is relaxation time. Relaxation time. Time. What is the unit of time? Seconds. So this is your answer. So by just practicing this problem, you became now familiar with this expression. Rho is equal to m by n e square tau. Okay. So this is the problem. Very simple problem. So like this, in your board exam, how you will be getting the question means define relaxation time. One definition will be there. Along it will be followed with what is the mobility of the electron and what is the mean distance. So after this small theoretical question, it will be followed with a small problem like this. Okay. So at that time we have to remember these formulas or expressions. Okay. So just pause the video and take the screenshot of this. And here are two more numericals for you here. So here, to calculate the mean free path. It should be as a mean free path. In copper, that average time between the collision is 2.5 into 10 to the power minus 14 seconds. And the average speed of the free electron is this much, it is given. Okay. So we have to find the mean free path. That means how it is denoted? Lambda, mean free path. And the average time between the collisions, it is denoted by the relaxation time, tau, is 2.5 into 10 to the power of minus 14 seconds. The average speed, you can take it as the average speed between the collisions, that is the drift speed, is 1.6 into 10 to the power of 6 meter per second. So now we don't have any relation connecting this as according to the given formula here. But this is very simple here. It is the distance, time, speed. Distance, time and speed. Distance is equal to speed into time. So you can apply this. The very basic formula. So lambda is equal to Vd into tau. Vd is 1.6 into 10 to the power of 6 and your tau is 2.5 into 10 to the power of minus 14. By calculating that, you are going to get it as 10 power minus 18. We found the distance, isn't it? So meter. So that's the problem. A very simple problem, and where the simple relation what we use, this distance is equal to speed into time. So lambda is equal to Vd into tau here. Okay. Coming to the next problem. Here the problem may be looking very big, but the solution will be very easy. As we have seen in our 11th class also observed, if the problem is big, it means much data will be given there. If the much data is given, you can no need to go for a search for the data. There yourself you can find the data and you can go with the problem. Everything will be given there. Only thing is applying the formula or just taking the formula, necessary formula, and just going for substitution and coming out. That's all. Okay, now look into the problem here. In a silver wire of uniform thickness, an electric field of 1 volt per centimeter. So electric field is 1 volt per centimeter it is given. So we generally go with a SI system, isn't it? It should be as a centimeter. It should not be a centimeter, should be converted to the meter. So it is 1 volt by 1 by 100th of the meter. So this 100 goes to the numerator, so it becomes 100 volt per meter. So this is our E. There itself we have changed. And is applied. Find the drift velocity and mobility of electrons. So the two things are asked here, drift velocity and mobility of the electron. Both are asked. Silver has some data is given here. Silver has 5.8 into 228 conduction electrons per meter cube. That means N is given. So N value is 5.8 into 28. No need to write the number because per meter cube, no need to mention the number. And resistivity rho, it is 1.5 into 10 to the power of minus 8 ohm meter. At 300 K, at 300 K means at room temperature. So here we don't have any use with the temperature, so we are keeping it aside, so no need to consider that. And the charge of the electron, even though if it is not given, we have to write this because it is necessary. Whenever we talk about the drift velocity or mobility of the electron or relaxation time, we have to certainly go with this charge of the electron, and if necessary, mass of the electron also. I think we don't find any use with the mass of the electron. Okay, and here, look at it, here one more, using these two, I can write one more expression here. So this E, tau and M is mu, isn't it? E, tau and M is mu. So Vd is equal to mu E. Vd is equal to mu E. That means just using these two, I have just got an expression connecting drift velocity, electric field and mobility of the electron. So this is all thing. So let us add this here. Vd is equal to mu E. Okay. So now if I want to find Vd, drift velocity, I should know mu. So here, how to get this mu? If I want mu, I need relaxation time. Look at the formula here. Mu is equal to E tau by M. So here I need the relaxation time, but I don't have a relaxation time here. But I have resistivity. I don't have relaxation time, but I have resistivity. Now, when I look at the resistivity, there is relaxation time, isn't it? So now I can make this expression relaxation time to resistivity. The resistivity is given. Now I'll just make these two as an expression for relaxation time. First of all, let me write the equation. You'll understand that rho is equal to M by N E square tau. Now tau is M by N E square rho. Okay. So now in the place of tau here, I will just substitute this. So what it becomes here, so mu is equal to E, instead of tau, M by N E square tau. Rho, divided by M. This is just instead of mu, tau, instead of tau, that was that I wrote M N square by tau. So now it is E, it cancelled, and this becomes M by M N E rho. So this M gets cancelled, so mu is equal to 1 by N E rho. So now your expression is completely turned to the whatever you have. So mu is equal to N 1 by N E rho. So N we have, E we have, rho we have. So substitute that mu is equal to 1 by N. What is N here? 5.8 into 10 to the power of 28 into E square. E is 1.6 into 10 to the power of minus 19. And rho, what is rho? It is 1.5 10 to the power of minus 8. So if we go for a calculation, we will get in the answer as 6.99 into 10 to the power of minus 3. So we are calculating mu, isn't it? So it will be meter cube per volt second. Okay, so that is about the mu. After getting mu, your problem became easier. Now just only going with finding Vd. Vd is equal to mu E. So Vd is equal to mu. We have calculated here 6.99 into 10 power minus 3, and E is how much we are having E? 100 volt per meter into 100. So we are getting this as answer as here it is 0.699 We are calculating Vd means velocity. It is meter per second. That is your answer. Isn't it? So this is a simple way. Just using one or two formulas and using the data, just finishing the calculation. Okay. Now take a screenshot of this. Okay, now after this numerical, we are going to talk about one very important concept. EMF and terminal voltage. Of a cell or a battery. This is a concept what you have to understand. So, just already you know about this, but a picture is to be formed in your brain regarding this EMF and terminal voltage. So let us understand what is this EMF and terminal voltage here. So suppose if you are having a cell or a battery, just we denoted this with the symbol of this is cell is shown like this, positive and negative. And if you connect a voltmeter, now this shows a reading, and that reading we will be calling it as the EMF, denoted by E. Isn't it? And what is this EMF means? Just the elaborated form of this electromotive force. By looking at this, many of you get confused, thinking that this is a force. But this is not the force. Just it got the name like that because it is understood initially as a driving force. So that's why just they came it as electromotive force. Electrons motivating force, driving force. So it got the name like that. But actually that is not the meaning of that electromotive force. It is not a force actually. So just to define this, you might have learned it as it is the work done per unit charge. Work done per unit charge in moving charges around the circuit. So this is the work done per unit charge. A lot of difference is there between these two. Electromotive force, whatever you call it as the force, and this is actually what it is, what it should be. Okay. Anyhow, suppose if you just take a cell, what you know, the electrolytic cell. So in this you will be having two electrodes, one the positive one, other the negative one, and you will be having the electrolyte in this. And now if this is connected, so now the charges will be going from the positive to negative, isn't it? So here initially, if you just look at this, what do you call it as the diagram here. Now, when this is connected to the external circuit, and if this is connected to what do you call it as, suppose if you just say here, initially it is EMF is E, and if you connect this with a voltmeter here, the reading will not be same as this E. So here, the V reading you will be getting less than E. That means this V, whatever it is, when it is connected in a circuit, it is not same as the EMF E. So this V, when it is connected, when the cell is connected in the circuit, we will be calling it as the terminal voltage. So what is the EMF of the cell means? It is the potential difference between the electrodes when the cell is in the open circuit or when the current is not flowing in the circuit. So you can understand it like this. Suppose if a cell is there and you are connecting it to an external resistance, and I'm using here a plug key. So no dot is there inside this. That means it is open. Circuit is open. No dot, circuit is open. No dot, circuit is open. That means the current is not flowing. So now if you connect a voltmeter here, it shows the reading, and we call this as the EMF of the cell. That means, what is this EMF? It is the potential difference between the electrodes when it is in the open circuit. That means when the current is not flowing in the circuit, or is not flowing in the circuit. Suppose if the current is flowing in the circuit, how can I show this? You just put a dot here. That means the circuit is closed. Now see the reading in the voltmeter. It will not be E. It will be less than E. That means I'm just showing it as the V. Now this V we will be calling as the terminal voltage. So EMF, when the cell is the potential difference between the maximum potential difference, that EMF is the maximum potential difference when the cell is connected in the open circuit. That means when the current is not flowing in the circuit. And when it is circuit is closed, the potential difference between the two terminals, or the two electrodes, will be as the terminal voltage. So now here, in this terminal voltage here, we understood that terminal voltage is V and it is less than E. And how much drop is there in that? How much? This is saying that some value is lost, isn't it? So where that value is lost? So here, when I just take a cell or a battery here, so in a cell, electrolyte will be there, electrodes will be there. So in this, because the electrodes and the electrolytes are the materials, electrolytes will be having ions. So when the current passes through this electrolyte, they get ionized, and because of these ions, collisions will be there, and because of the collisions, resistance is there. So because of the electrolyte, resistance is there. And at the same time, electrodes are the materials, they will be having resistance. So because of these electrolytes and electrodes, some resistance is there, which is not allowing the charges to flow freely. So there some potential drop is there. So because of the resistance inside the cell, what we will be calling here it as the internal resistance of the cell, there is decrease in the potential. That means we will be calling this as voltage drop or drop volt. So voltage drop will be there. So now here, from this discussion we understood that the cell or battery is having some internal resistance. So how can I show this cell or battery is having some internal resistance? Means here, this we will be calling it as the cell, showing this is shown as the cell. And if we just leave it like this, that means we are not considering any internal resistance. Up to 10th class, the cell means you just wrote it like this. That means you are not considering the internal resistance. But here, we have to consider the internal resistance. So what I will do is, after writing it as 6 volts or something, I will write R here. That means I am just showing that it is having some internal resistance R. This is one way of representing. The another way is this one, and a small resistance in series with that. So this is R. So like this. So most probably this is not used, and this is used to make you to understand clearly that the internal resistance of the cell is R. So I am taking this and forming a circuit. The external resistance R like this, and a key. Now it is opened, and if I connect the voltmeter between the two terminals here, and I am getting the maximum potential difference E, and if it is closed, the potential difference is V. And we came to know V is less than E, and some potential is lost. We will be calling this as the drop voltage. How much the last voltage is there? How much voltage is lost? So to find that, how much voltage is lost here? So V is question mark. So let me take this as the last volt as V dash. That's the better to make this here, V dash. How much last volt is there? You apply Ohm's law. What is the current flowing in the circuit? I. I is the current flowing in the circuit. So if the I is current flowing in the circuit, here it will be I, here it is I, here it is I, here it is I, because they all are in the series. So the current remains same. So here also the current I is there. So what is V here? By using Ohm's law, V is equal to IR. So V dash is equal to, so here I taken this as the V dash. So it is V dash is equal to I small r. So this is the last voltage here. So now here V is equal to E minus IR. So this is, we will be calling it as the terminal voltage. So the terminal voltage is given by the EMF E minus IR. Okay. So always, so you can go, we can understand, or we can come in reverse manner and we can understand it in another way also. If the circuit is open, how much the value it shows here E, that we call it as the EMF. And I told you that is the maximum potential difference between the two electrodes when the cell is in the open circuit, right? So now, now in the open circuit, what is I? I is 0. If I is 0, what happens to this expression? 0 into R, because this becomes 0. So V is equal to I. So this is the maximum. So by this you can understand that what is the terminal voltage and what is this one here. And coming to the internal resistance of the cell. The internal resistance of the cell. The internal resistance of cell here. Already we just had a small discussion regarding this. We just consider a cell or a battery and just to break it open and see. There you might be seeing some chemicals and a graphite rod or a zinc plate, and all these things you can see in the dry cell. And in batteries you will be having plates will be there, and between the liquid will be poured, and so there electrolyte is there, electrodes are there, so they offer the resistance. So that resistance we will be calling as the internal resistance of the resistance offered by the electrodes or electrolytes of the cell is called as the internal resistance of the cell. So here the important thing what we have to understand is what are the factors that influence the internal resistance of the cell. So the internal resistance of the cell depends upon the distance between the electrodes. So it is the distance between the electrodes. Distance between the electrodes. How this influences the internal resistance? How the distance influences the internal resistance of the cell? If the distance is more, so here they have to travel for a long distance. So that means the resistance increases. So when the distance increases, the resistance also increases. So R is directly proportional to B. So this is one factor. And number 2, and area of the plates or the electrodes, this also influences. Suppose if you are having an electrode like this, so it is dipped in the electrolyte. Now in the electrolyte the ions are there, and the ions will come and collide to this, and thereby the charges get accumulated on these electrodes. The ions in the electrolyte come and just collide with this electrode and get accumulated. On this the charges get accumulated. This is the way. So if this is the surface, just compare with these two here. So this is having less surface and this is having more surface. Less surface, less collisions, so less accumulation. More surface, more area, more collision, more accumulation. So that's what happens here. More area, less resistance, less area, more resistance. So from this we understood that here, how this is influencing means it is 1 by A, inversely proportional. Okay. And the other one is nature of the electrolyte. So whenever the electrolyte changes accordingly, the resistance, the internal resistance also changes. And the concentration of the electrolyte. These are all the important points for your a good question for your board examination. So just might have to take it into your mind. Concentration of the electrolyte. More is the concentration and more will be the resistance. So resistance depends upon the distance, area of electrodes, nature of electrolyte, concentration of the electrolyte, and the other one is temperature. Temperature also influences. Temperature. Temperature here, before giving the explanation, we just will go with a very with a live example, whatever you might be experiencing during winter season or during the cold seasons. Early morning, you just try to just start your bike by pressing the button. It won't start generally. So it means that the charge the battery is providing is not sufficient to operate the engine. That means there the resistance by the electrolyte is more. Less the temperature, more the resistance. So during the winter season, the temperature will be less. So the internal resistance of the battery is more. So if the internal resistance of the battery is more, the current will not flow freely. If the current will not flow freely, the current is not sufficient to run your engine. So this is inversely proportional. The temperature inversely proportional to the internal resistance. And similarly, we can go with one more. It is number of ions. Number of ions also will influence the internal resistance of the cell. So these are the factors which influence. And simply here we just talked about what is EMF. And by how much the potential will drop at the internal resistance, and what is the last volt, and what is the relation between terminal voltage and EMF V is equal to E minus IR. And here one important question here, when the EMF will be equal to the terminal voltage. When the EMF will be equal to your terminal voltage. So when the circuit is open, then your V value will be equal to E. And here one more question is there. Here we said that V is less than E always. Is it true always? Yes, it is true always except one case. What is that case? Where the V is greater than E. Here, in all these examples here, the battery is getting discharged. The battery is getting that means the battery is providing the electric current. So after a long duration, what happens? The charge will be going away, and no more the process taking place in the within the electrolyte is not able to provide the sufficient energy to make the electrons make the charges to accumulate on the electrodes. So there, that means we say that the battery is dead. So now what we have to do, we will charge the batteries. So during the charging of the batteries, your V is equal to E plus IR. During discharging, V is equal to E minus IR. While charging, it is V is equal to IR. Okay. So this is now I just gave all these things in a simple explanation, and in the next session we'll go with a little more elaborated way how we get this V is equal to I minus R. So here, anyways, here remember here the formula V is equal to E minus IR. V is the terminal voltage, E is the EMF, and V is equal to E plus IR is for what you call it as the charging. Okay. So this is these are the things what you have to remember. Pause the video and take the screenshot.